I'd like to call the meeting to order. This is our weekly M-Cube seminar. Today we have M-Cube's own Falko Judt. And, Falko's, did I get that right? Okay. Falko has been a scientist at M-Cube since 2018. Falko has a PhD from the University of Miami back in 2014. He came to NCAR as a ASP postdoc in 2016 before joining M-Cube as a member of the permanent staff. Falko's interests are in tropical meteorology, especially hurricanes and atmospheric predictability. And his 2018 paper on the subject received the UCAR Outstanding Publication Award. More generally, he's interested in the science behind weather prediction, especially of extreme weather. Toward that end, he's been investigating the potential of global cloud-resolving models to predict weather from local to planetary scales. Appropriately, his title today is Improving Tropical Weather Prediction and Understanding Tropical Cyclone Intensification Using Global Convection-Permitting Models. Welcome.
Yeah, thanks, Rich. Some of you probably know I gave an M-Cubed happy hour 4 weeks ago, and if you were there and you didn't like it, you're in luck because there's no overlap between the stuff that I showed there and what I'm going to show here. So what am I going to show here in this talk? I tried to condense it into a title, and the title is a little bit bulky. And that's because I'm doing a lot of things slightly orthogonal sometimes, because my work here at NCAR has really been shaped by a tool, not by a science question so much, but by a tool that is global convection-permitting models. And these models are an awesome tool, really, because they give us a picture of the atmosphere more realistic than we have ever seen before. We have access to the global mesoscale. In this animation here, from a 3.75 kilometer MPAS run, you can see hurricanes spinning here. You can see mesoscale convective systems in the ITCZ over the Amazon region. But you can also see extratropical cyclones and cold air breaks well, it stopped animating, but there were gravity waves over the Andes here. So it's a look at everything, and you get lost in it, really. My work is really about what these models are capable of doing and other science questions that I will talk about today. Well, why isn't everyone in M-Cubed using global convection-permitting models or global LES simulations if we look decades into the future? The main reason probably is because global convection-permitting modeling is still costly, even if we take into account the increase in computing power, and I want to illustrate this. If you were to take MPAS, atmosphere, our in-house global model, straight out of the box, and you run the 120 kilometer grid spacing mesh for 24 hours, that costs you about 2.5 Cheyenne core hours. So I use this because this is typically what climate models are run at, so about 1 degree or about 100 kilometers. Now, numerical weather prediction in its operational sense, that's about 10 to 15 kilometer grid size. Again, if we take MPAS and we run it for 24 hours, that costs 2,000 Cheyenne core hours. So if we double the resolution again, we land at 7.5 kilometer, and then again we go to 3.75 kilometer, which is the resolution that I've been running. And if you're interested in the cost, that's what it is for 1 day. This is no surprise to us, right? Because we know every time we're having the grid spacing or we're doubling resolution, compute cost goes up by a factor of 8. So to go from here to here, you're actually, this is a factor of 32,000, roughly. And in theory, and actually, it's pretty close to that in reality. So of course, we need to show that there is actually some value in this, right? This is really expensive. You can convert these numbers to dollar values. And it's no joke running a 3 or 4 kilometer global model. So a lot of my work really is trying to tease out what is the added value, what can we learn from this simulation compared to, for example, this simulation, global simulations of 15 kilometer grid spacing or climate type simulations. And so the first part of my talk is really about the added value, or model fidelity, you can phrase it in that way, or how much return on investment. So again, these simulations are costly. We want to learn how much better are they than what we're used to. And the first part here will focus on tropical weather. That's where my scientific interests lie, somewhere here in the tropics, where we have hurricanes, but also equatorial waves and a lot of interesting stuff. So to look at the added value, or how much better is a 3.75 kilometer simulation compared to a 15 kilometer simulation, we're creating the MPAS resolution ensemble, and this was our contribution to the diamond intercomparison. If you're not familiar with diamond, it's the crown jewels of atmospheric modeling. It's an intercomparison of global convection-permitting or cloud-resolving models. It stands for dynamics of the atmosphere modeled on non-hydrostatic domains. So again, we're in NCAR, M-Cube, we're using MPAS. And this is the resolution ensemble. So it has 10 simulations that only differ in mesh spacing. The vertical grid is the same, the physics are the same, and we're starting with the nominal run here. This is the gold standard, the 3.75 kilometer run. And we're doubling resolution, and we're going all the way out to something that's probably a climate model from a few decades ago. So I should say here, for these simulations, we're using Wei Wang's scale-aware Tiedtke scheme. So that means we're using a cumulus scheme, but it's scale-aware. So it's mostly shut off here, and then it turns itself on if we're going to lower and lower resolution. Come back to that later. So 10 simulations that only differ in grid spacing. We're running 40 days. One simulation out to 40 days, August, September 2016. And the initial conditions and the SSTs are coming from ECMWF. So the model setup and the way we handled the simulation was determined by the diamond intercomparison the way they wanted it. So this period was run by many models with the same initial conditions and SSTs, and I'll show some results of this model intercomparison towards the end. In the interest of time and to make it a little bit less dense, we're just going to focus on 3 simulations here, compare these 3. The 3.75 kilometer run, this is, again, the gold standard. This is what we're hoping that the future of NWP and climate modeling looks like. This is standard NWP now. The GFS or ECMWF are here. And this is CMIP type climate models. So that's why I picked those 3. Okay, so let's just jump right into the results. What I'm showing here is a Hofmüller. If you're unfamiliar with Hofmüller, it's a time longitude diagram. And we're usually using this for tropical precipitation to show propagating features. So we're averaging precipitation in a 10-degree belt. For this period, it was between 5 degrees north and 15 degrees north. We're averaging the precipitation there, and then we get slices. And every 6 hours, we get a new slice and build this Hofmüller. And it shows you that in the tropics, the weather isn't boring. There's actually a lot of variability, a lot of stuff going on. And this is what the 120-kilometer MPAS produces. It looks qualitatively very different. You have much fewer of these propagating features, and the precipitation is just anchored over the Indo-Pacific warm pool. So this is typical of models with cumulus parameterization.
What's the gap?
This is the eastern Indian Ocean. During the summer, that's where the monsoon winds turn, and there's no precipitation. That's east of Africa, so Somalia towards the middle of the Indian Ocean. Yeah, so that's just a dry period during that time of year. So again, that's the 120-kilometer MPAS run. This is 15 kilometers. not much different, not much improvement, right? Going from 120 to 15 kilometers. But what we're getting when we go to 3.75 kilometers, obviously much closer to the observations. So this is what we want to see, because now we can make an argument. There's actually return on your investment. It makes sense to run a 3.75 kilometer global model because obviously it gets much closer to the observations. This is, to me, that's actually one of the money shots here, because there's clearly a step change going from 15 to 3.75 kilometers. And on the bottom here, we see the amount of precipitation that's coming out of the resolve scale, so the microphysics. And for this simulation here, it's almost all of the precipitation is coming from the microphysics scheme. So the cumulus scheme, again, it's scale aware, so it's still a little bit active, produces about 12%. But here, the cumulus scheme produces 100% minus the number that's indicated there, so it produces almost everything. And to tell you that to show you that it's not only the fact that we're increasing resolution, it's really the fact that we are resolving convection or having explicit convection comes out when we repeat this simulation, and I did this by accident, and turn on the full cumulus scheme, and this is what you get. See that? So between here and here, the only thing is the cumulus scheme is fully active or just a little bit active. Okay, so that is the overall precipitation. Now we can filter this precipitation field for equatorial waves. And I'm going to show here Kelvin waves. So it's the same underlying data. We're just running it through a Fourier transform in time and longitude. And we're filtering out certain features. And this is Kelvin waves here. On the left, the observations from iMerge. And here the three simulations. You can probably not tell that there's a big difference, and in fact there isn't. So Kelvin waves are handled well by MPAS even when you have very coarse meshes. Now we're going to tropical depression type waves, also known as easterly waves, and now we're filtering the underlying precipitation field, and now we're seeing, well, this 3.75 kilometer run with mostly resolved convection is much closer to the observations than the 15 and the 120 kilometer simulation. And then last but not least, this is the elusive n=1 westward inertia gravity wave. You don't have to worry about it too much. It's a feature that lives along the equator, it lives in the tropics, and it produces rainfall variability. But the point here is compare observations with the model simulations, and clearly only this one comes close. So there's a clear tendency for the convection-permitting model to produce something closer to observations than all the simulations with parameterized convection. And again, to make this point very clear, this is how the inertia gravity wave looks like in the 3.75 kilometer run when the cumulus scheme is fully active. So looks good, looks bad, looks good, looks bad. Okay, so that's all very qualitative eyeballing, but I think it tells we don't need more, but let's be a little bit more quantitative here and boil it all down into numbers. So this is the variance of precipitation. This is just the variance computed directly from the Havmüllers. Yes?
Yeah, can you go back a slide just for a second? I was just curious, in the run that you said you did by accident.
Yeah.
So you are resolving the convection and the cumulus.
Yeah. So the assumption to have a cumulus scheme kind of breaks down. Yeah. So it was purely an accidental run, but it shows us that it's not the fact that you're going to higher resolution, but that produces better results, but the fact that you're letting the model develop the plumes and the convection explicitly rather than having it parameterized, even though you probably don't want to have a cumulus scheme at 3.75 kilometers. It's accidental, it just illustrates a point. Now going back to, this is, the bars show you the variance of precipitation in the tropical region. On the left here, that's the observations, and clearly it's only this simulation that comes close. We're still missing a bit, so we're not perfect, but obviously much better than this, and we see what we want to see, the step change behavior. I like to see the step change behavior that we can really justify having super expensive simulations. Filtering it for the three different wave types shows the same picture. that Kelvin waves, easterly waves here in the middle blue, and inertial gravity waves in the light blue. And just comparing the bars there, clearly this run does much better than the other two. Digging a little bit deeper now into equatorial waves, we're going to be looking at rainfall anomalies associated with waves and the vertical structure of the waves. And the way we do this is by a method that Rosie came up with. So we're essentially pretending we're at a fixed location in space, and we have a wave propagating over us. And so we're one of these dots in this figure here, and the colors denote time. So the wave is propagating over us, and what we could feel if we were at the bottom is, well, when we're in the gray area, this is the suppressed phase of the waves. There's a negative rainfall anomaly, and the wave phase here, you can correlate that with the colors on this diagram, which is like a clock, and the location here. We go towards the convectively active phase. The peak is at wave phase 5, which is right in the middle here. So this greenish here represents the 5 here, and then the wave passes, and again, we go into the next trough, into the next valley, which means here suppressed precipitation. So how does it look like for this 40-day diamond simulation? Each panel here is a different wave type: Kelvin wave, easterly wave, or tropical depression type wave, and inertial gravity wave. The black line here is the observation from satellite estimated rainfall. Let's start with the green line here. It's not 120 kilometers, actually 30 kilometers, but it doesn't really matter. It's where we have mostly parameterized convection. And you can see, well, it kind of captures the waves, but the signal is washed out. So it cannot discriminate very well between the active phase and the suppressed phase, as we see in the observations. Now we're going to 15 kilometers. This is your standard GFS resolution. It's not much better. And now we're making the big step. It's almost too good to be true, right? So this model is totally untuned, but it really captures the rainfall anomaly very, very accurately for all the three wave types here. If you compare the purple from the 3.75 kilometer MPAS to the black, which is the observation. So very encouraging results if you're a weather forecaster in the tropics and you're looking towards the future of numerical weather prediction in the tropics. So now moving on to now a vertical cross section here. So on the y-axis we have pressure, so this is our vertical coordinate. And on the x-axis, we have wave phase. This is just, now on the left here, we have the observations, quote-unquote observations. We use satellite estimated rainfall and era 5 for the other fields. In contours here, this is a vertical velocity from era 5. And in the colors, that is temperature anomaly in Kelvin. So this is just for inertial gravity waves, and we're comparing observations on the left with the convection-permitting MPAS compared with the 15-kilometer MPAS, which is mostly parameterized convection. And what you're seeing here, the pattern between panel A and B is clearly similar, but this seems much more bold than in the observations. So what the bottom line here is the 3.75-kilometer MPAS seems to get the pattern right in terms of, so this is a westward moving wave, so we're starting out with a warm anomaly at the surface, then we get upward motion, and then we get the cold pool here. The model captures that, it's just much stronger, and we're not sure if maybe the reanalysis is not representing reality, or maybe there's actually a bias in the model. So we're not sure because we don't have actually observations that are commensurate with a global grid of 3.75 kilometers other than relatively coarse resolution reanalysis. So this is a different field now, but same thing, wave phase. So we're standing here and we have the wave propagating over us. In colors now we have vertical velocity, and you can see this tilted structure. So in wave, the vertical velocity becomes positive first in the lower levels and then transitions towards the upper levels. So the 3.75 kilometer MPAS shows that as well, this tilt. And this version of the model cannot capture that tilt. So clearly, this this parameterized convection simulation seems to be matching the amplitude, but it doesn't match the structure, the vertical structure, right? And lastly, this is the same type of diagram just for humidity in the colors, and we're seeing this tilted structure again. First, we have moisture in the lower levels, and then the wave peak passes and it transitions to moisture in the upper levels. And the pattern looks very similar in the 3.75 kilometer MPAS, and in the 15 kilometer MPAS, it just doesn't capture this vertical structure of the waves. That's probably one of the reasons why the model with parameterized convection does not capture the waves in general. So before we move on, I want to present some bulk statistics or bulk metrics now, again, looking at model fidelity, added value. This is rainfall intensity it's essentially a histogram. So on the x-axis, we have rainfall intensity in millimeters per hour, and on the y-axis, we just have pixels that we count. Black is observations. We have few pixels with high rain rates and much more pixels with lower rain rates. So that's how this figure should be interpreted. This is what a climate type model gives you. This is what a NWP type model gives you, or MPAS emulating an NWP type model, and this is the convection-permitting MPAS. And clearly, we're having this step change again, being much closer to the observations. Then we're using the full Tietke scheme again, and we're losing all that benefit. It brings us to a much lower resolution of the model. Last figure here, this is the rainfall rate versus saturation fraction. So how much does it rain given a certain vertically integrated saturation fraction? So this is essentially your relative humidity vertically integrated, and we can see that there's this clear exponential increase towards higher humidity gives us stronger rainfall rates. This is the 120 kilometer MPAS, or 30 kilometer MPAS, 15 kilometer MPAS, and this is the 3.75 kilometer MPAS. So obviously, much better, getting closer to the observations. This is what we want to see. So I want to close this part of the talk here with a one-liner. So I think what we can see here, or I think you're convinced that MPAS with explicit convection, so a 3.75 kilometer grid, improves the representation of equatorial waves and rainfall. And the reason is explicit is better than implicit. That's the main message here, that we're resolving convection, we're letting the equations do the work rather than a parameterization, and everything seems to fall into place. So briefly now towards the second topic in the added value part of this talk. So we're looking at tropical cyclones now. These are the 24 tropical cyclones in terms of their tracks that were observed during the diamond period. Again, that was August, September 2016. And this is what the 120 kilometer MPAS gives you. It doesn't capture any of the Eastern Pacific hurricanes, for example. This is what the 15 kilometer MPAS gives you. It trends in the right direction, but still misses quite a few of them. And then almost magically, you're running a global model at 3.75 kilometers, and you're almost getting the exact number. So that's probably more luck than anything else, but I think this trend is encouraging, going from climate model resolution towards convection-permitting resolutions. You're really starting to capture the mesoscale that's out there, in this case, tropical cyclones. It's more important, though, I think, in intensity, because that's where the models are struggling in general, not so much the number of tropical cyclones, but really how strong the TCs are. This is a time series of 40 days here, and each black line is the intensity time series of these 24 observed cyclones. So on the left, we have the maximum wind speed in knots. On the right here, this is your well-known Saffir-Simpson categories. So if you're not a TC person, you probably still know these numbers here. What we're seeing, there was this period of elevated activity towards 3 to 4 weeks into that diamond period, where we had a bunch of strong typhoons in the Pacific. The 120 kilometer MPAS does not capture that. It's not supposed to. Remember Chris Davis's talk a while ago, he was showing exactly that. 120 kilometers, you're not resolving the inner core of a tropical cyclone, so you're not capturing the intensity. 15 kilometers MPAS, you're getting there, but you're clearly low bias, right? So the gray lines here are the black lines up here, just to make the comparison easier. And we're doing much better when you're going to convection-permitting resolution. And what I find fascinating is that the model seems to actually be able to capture this peak of activity that's 3 weeks into the run. That's well beyond the day-to-day predictability. To summarize all the spaghetti plots that I showed, we can look at the accumulated cyclone energy. That's a metric that integrates the total energy output of the tropical cyclones, and observations are here in gray with some error bars, and the 3.75 kilometer MPAS actually does overshoot a little. I'm not too worried about that because this is without active ocean coupling, so if in reality a tropical cyclone, when it's very strong, it brings up cold water from underneath, and that acts as a brake on the intensity of the cyclone. We don't have that effect here in the model because we're using prescribed SSTs. Don?
Is that just the kinetic energy?
This is, it's a very awkward quantity. If you see here, it's in
Could you
10,
repeat the question
10.
for the folks back home?
Okay, so Don Lenshaw was asking if this is just the kinetic energy. It's essentially for every 6 hours, we take the peak wind speed, and we're adding all those 6-hour increments of peak wind speeds that the storm has at the time together. So it's not really the integrated kinetic energy of the whole wind field. We're just using the peak wind, which is the metric that hurricane scientists you like to use. And then we're adding them all together, and we get this awkward 10 to the 4 knots squared. So I think I showed this TC stuff before. That's why I want to make it short here. The bottom line is that 3.75 kilometers, so a global convection-permitting model, reduces this long-standing bias of global models not being able to capture the structure and intensity of tropical cyclones. Okay, so now we're going to switch gears quite a bit. Now we're going from model evaluation to actual science understanding. What we're going to be looking at is now rapid intensification of tropical cyclones, and not all of you are hurricane scientists, so I'm giving a definition of rapid intensification. Is one of the big questions when you're in the hurricane community. So rapid intensification is a phenomenon when a tropical cyclone undergoes a significant increase in strength over a short period of time. It's shown here in this figure. On the x-axis, we have days. It's relative to when rapid intensification starts. And here in the black line, that's the maximum wind speed. Numbers are on the left. And in red, this is the minimum pressure in the eye on the right. And you can see it's slowly intensifying, and at some point, it just hits the accelerator. And really, this is the period of rapid intensification where we have a much stronger increase in intensity. And the magic number that the operational forecasters looking at to define rapid intensification is 30 knots, an increase in the maximum winds of 30 knots, that's 50 meters per second in 24 hours. So I used the diamond simulation essentially as a test bed, not as a test bed, but as a data source, and mined it for the tropical cyclones and checked each tropical cyclone if it matches this rapid intensification criterion, the 30 knots in 24 hours. And there's 23 total tropical cyclones in the simulation, and 7 of them meet this criterion. And they're plotted here in black, that's maximum wind speed, in red, that's minimum pressure. And I didn't put them in this pattern randomly. On the top here, this is actually when you look at just the rapid intensification period, we see this more or less steady increase. There's noise, clearly, because this is a turbulent thing, a hurricane, but its pressure is steadily dropping and maximum winds are steadily increasing. It's more clear in this archetype here than in the others, but it's still qualitatively different from the cases down here where we have this jump. There's not, you cannot really draw a trend line through it. It's more like suddenly there's a jump in intensity. So a drop in the pressure and a rapid increase in the maximum wind, and not really this longish trend. To contrast these two types of rapid intensification a little bit more, I'm going to be focusing now just on the archetypes, the two examples that embody these characteristics the best. And when you look at the intensification, again, this is all relative to what we call RI onset, the beginning of rapid intensification. On the left here, this is the intensification period is long-lasting. It lasts actually 2.5 days. Here, it's a matter of actually hours. The intensity jumps within 3 hours, so it's a short-lived intensification burst. Moderately paced versus instantaneous. On the left here, this is actually, we're starting out as a tropical storm here, and we're ending 2.5 days later as a strong Category 4 storm. The y-axis here is different, so this is a little bit confusing, but this jump, even though it meets the RI criterion, the 30 knots in 24 hours, it only gets to a minimal hurricane, so a Category 1 storm. If you're looking at all these qualities, actually George Bryan came up with a great analogy. So he said, on the left, that looks like a marathon, right? And here, this is more like a sprint. And so we stuck with this analogy, and the paper's actually named like that. But I want to give credit to George. He came up with this analogy. The interesting thing is that these seem to be fundamentally different pathways of intensification. On the left here, this is surface winds. So this is 10-meter wind speed colored in the magentas, and the black lines, that's sea level pressure. This is your canonical hurricane. The bullseye, this is with the calm winds in the center, and then the whole thing just keeps intensifying and keeps intensifying faster. That's rapid intensification in the RI mode. This is actually the canonical case. So if you run idealized hurricane simulation in, for example, Georgia's CM1 model without shear, or just over a warm ocean, you get this pattern, this intensification pattern. The sprint mode seems to be very different. It's kind of messy. We're starting out with a sprawling gyre. So instead of a tight circulation, tight weak circulation, we have a weak sprawling gyre. And at some point, there's a convective burst. And this burst, within a few hours, spins up a new center that then intensifies very quickly. So spin up happens within a couple of hours, not the whole gyre, just this new feature inside the gyre. And this is a center reformation, as we call it. But here, it also means it matches the rapid intensification criterion. And to show you that it's really a convective burst, I'm showing the sequence here on the top here. This is, again, the wind speeds in the magenta, and down here, this is radar reflectivity. So we have this jumble of contours here in the southwestern quadrant of the circulation, and that's just a reflection of this convective burst. So this is actually 100 kilometer or hundreds of kilometer MCSs just erupting and bubbling about. What happens, though, at some point is it spins up this really tight mesovortex. So this is a feature that's 50 kilometers across, and it's clearly associated with this mesoscale convective system here. It's almost like a supercell. So it's a rotating updraft that spins up in this vorticity-rich environment of the gyre, and then towards the end becomes essentially its own cyclone that lives in the parent circulation. So it's an interesting process. It's not the canonical TC spin-up process. I want to show this quickly here. This is about the environment these two rapid intensification specimens are embedded in. On the left here, this is the marathon RI mode, or the canonical, where we have here, this is the Vmax trace again. And in purple here, or in magenta, this is vertical wind shear. In the TC world, this is bad for cyclones. It tilts the vortex, it creates two downdrafts, and it shuts down that heat engine. And what we're seeing here in the canonical case, when RI, rapid intensification, starts, we're actually dropping in shear. It almost goes down to 0. So that's very low shear. On average, a 24-hour average around that RI onset is 4 meters per second. That's low shear. That's good. Not surprised this intensifies. But then here, for this case, the shear is larger than 10 meters per second throughout, and actually 12 meters per second. This is high shear. Nobody would expect this storm to undergo rapid intensification, and it's also in a much drier environment. So this environment here in green, that's the relative humidity in the middle levels. It's relatively moist for this case, so this is a favorable environment. This is an unfavorable environment, and yet the storm manages to experience rapid intensification because of this mesoscale convective, or mesovortex that develops a convective burst that turns into a mesovortex and then spins up its own vortex in the parent circulation. And how does it do that? It just feeds on CAPE. So in colors here, this is CAPE, straight from the model, and this is your canonical case. So there is some CAPE, but in comparison, it's much less than in this case, the sprint mode. Here, this jumble of contours again, this is that convective burst. So it's essentially a bunch of MCSs, and if you follow the arrows here, which is the wind flow, it draws this very juicy Cape-rich air into that convective burst, and because of the sprawling circulation, there is just a reservoir of a lot of CAPE, and that keeps this burst going, and so the storm manages to intensify even if the environment is less than ideal. So we wrote this paper, we submitted it, and we got reviews back, and one reviewer was a little bit cranky and said, this is just a model, right? How do you know the model is right or wrong? And it was about this marathon versus sprint. And the reviewer asked us to look into observations, and we actually see it in observations. What comes out of it, if you're screening the observations, so the HERDAT2 database, and you go through all the tropical cyclones in the Atlantic that have been observed, and you're screening it or you're filtering it by how many RI periods, successive RI periods there were, you get 57 hurricanes that follow this RI mode, and then almost the same number follows the sprint mode. And you can clearly see, they're different. That I'm highlighting two prominent examples here. And then in red, this is the archetypes that came out of the simulation. So Rosie actually threw a Jupyter notebook together really quickly to data mine the observational database, and we were really happy that it's not a fluke of the model. There seem to be these two modes in reality too. Nobody had really seen them, so I'm saying here, we discovered. It's a little, we kind of discovered, because the literature is agnostic about if there are different modes of rapid intensification or not. It's a very complicated topic, complex topic, but we think we found these two modes in this global convection-permitting simulations. Okay, so towards the last part now, this is the model intercomparison. So this goes into, I pretty much want to show that MPAS, all that stuff that I showed before looks great, but there's large intermodal differences or intermodal spread between a group of global convection-permitting models. There's about 10 to 12 centers that are able to run global models with 3-4 kilometer grid spacing, and this is the tropical cyclones that these models produce. Without going into details, you can see some of them are unrealistically strong, like this one here, or look really strange, like this one here in the SAM model. So all these models are based on the same equations of motion, but obviously they use very different physics. And the big hope of global convection-permitting modeling is that the models kind of come together, that we're getting convergence towards hopefully the truth. And I think it's not really happening. So this is a note of we should be careful. These models are great, but there's so much spread between them, and we don't know which model is the best. There's significant variability among the models. This is, again, your accumulated cyclone energy diagram in bars here, observations on the top. And then I showed MPAS before, but now MPAS is grouped with all the other models that use kilometer scale grid space. And you can see some models like ICON produce too little ACE, accumulated cyclone energy, and models like GEOS produce way too much. I'm going to skip this in the interest of time. I wanted to bring up the waves again. This is just copied from one of the first slides. This is the Hoffmüller diagram of the diamond summer period of all the waves. This is MPAS, so we have seen this. Let's compare it to the other models. And you can see they all look different. They all look different in their own way. For example, this model here seems to have a lot of rainfall. This is the Eastern Pacific intertropical convergence zone. So again, the bottom line of all of these figures is there is tremendous intermodal variability, even though they are all running without a deep convection scheme or a mostly inactive deep convection scheme. There's still a lot of variability. And just recently, I looked into the Diamond 2 simulation, which is also another 40-day run, but now for the winter. And if you compare observations from the summer to the winter, first of all, you see the wave pattern looks very different. This is MPAS. These are the other models. Again, they all look very different from each other. None of them look as bad as a model with deep cumulus parameterization, but there's still so much variability that I don't think we can conclusively say these models are converging towards the truth. And to summarize this, this is, again, the variance of the wave-filtered precipitation. So for each, there are 4 different equatorial waves, Kelvin waves, tropical depression type waves, mixed Rossby gravity waves, inertia gravity waves. Observations here on the left, and we would just want to do an eyeball comparison with the number of models. You can choose which one you like best. Morris, which one do you like best? MPAS. Well, it came out this way, right? But the point really is this, for example, GEOS. This is the model. It produced really great-looking tropical cyclones, and the structure looks great. But it cannot capture equatorial waves for some reason. The variability is just much different. So one model may be great at one thing. Other models may be poor at one thing, but much better at a different thing. A little bit concerning is that none of the models did well in the winter. So this is the variance of wave-filtered precipitation for that winter case observations, and there's clearly a bias. There's a bias here on none of the models get to the observational values, but this is really drastic here. This is a little bit disappointing to see that the models are not able to capture equatorial waves in the winter. Well, it's in the tropics, so summer and winter don't mean that much, but still, the intertropical convergence zone shifts, there's work to do, right? So running a global convection-permitting model, and you think we're now, I showed in the beginning, oh, we're doing much better with equatorial waves. That was kind of conditioned on the summer case. It looks much different in the winter. Okay, so to summarize this part of the talk, there's still this large intermodal spread. We're not really converging. That was one of the big hopes of Diamond, that we're coming closer to the truth. But I think we're clearly not there yet. And no model is really, you can say, the best. Some models do better than others. And it's also difficult to group by model bias. Some models are FE3 based, using the FE3 dynamical core, but they have very different physics, and they do very differently in precipitation variance versus tropical cyclones. So it's really hard to kind of group the models into camps. And that makes it harder to improve them. Okay, so in the last couple of minutes, I actually, this is my brainstorming part of the talk. I want to bring up a few challenges in global convection permitting modeling. I don't want to spoil this tool. I think it's great, but there are some challenges. The first one is that it's really expensive. So we can run 40 days. We have an ASD project on derecho. So the new supercomputer, the next generation of supercomputers, and we can run now almost close to a year, maybe 300, 350 days. But it's a big project. We cannot do climate timescales or ensembles. Clearly not feasible yet, and won't be for not with the red show, probably not with the computer that comes after that. And then even if computational resources weren't a problem, you run into storage and data analysis. They become problematic. So the diamond runs 40 days. We're outputting a lot, so it's 90 terabytes of output per simulation. You can still sift through that data in ways that, as I do it, but it's not ideal. So our tools that we're using are not really made for this amount of output. There are new analysis paradigms, new Python packages coming along, how to analyze unstructured data. But first of all, they are hard to learn. And hard to learn not necessarily in the sense of difficult to do, but the community hasn't agreed on what tools are best. So you could invest a lot of time and learn, I'm going to throw a name in here, UX-Array. It's a new Python package, but we don't know if UX-Array will be around in a couple of years. Maybe something else will be around. So hard to learn, meaning there's a lot of competing packages, and you would have to invest time, but you don't know if that's really the best tool or if there's going to be an evolution in tools. So this is a question that is always on my mind. So what science questions are we supposed to, or can we address with these models? Because in grad school, I did tropical cyclones, and using a global convection-permitting model, you're not just doing tropical cyclones or squall lines. So they're really not the right tool to study individual phenomena or processes, right? You don't run a 3-kilometer global model to look at squall lines. What we can do, though, is looking at the mesoscale, large-scale interactions. So this is something you cannot do with WRF, for example. How the mesoscale feeds back to the large scale, so these interactions. But coming out of the microscale and mesoscale meteorology lab, it's difficult to really, if you want to do it, how do you do it? How do you look at mesoscale, large-scale interactions? What the models are good at, they provide a look at the mesoscale in a global context. So you want to know about squall lines? Most of what we know is from squall lines over the US. Do squall lines in South America look similar or different? How about in the Indian Ocean? So a model like this gives you access to the whole globe. So it's comprehensive in the sense, more comprehensive than any regional modeling can do. One of the big pushes that the community of global convection-permitting modeling gets is the hope that we run these models operationally at some point, we get better predictability. So, for example, the argument often goes, if we resolve tropical convection explicitly rather than parameterized, we get a better mesoscale, large-scale interactions. Teleconnections are represented now in the model that weren't before. We can make longer-range S2S type predictions much better than we currently can do. However, to prove that, you need long runs in many cases and large ensembles, and then it goes back to point 1 very quickly. Because long runs, many cases, large ensembles with a 3.75 kilometer model is not going to happen anytime soon. We're working towards it. But so nonetheless, these are some challenges that we overcome. I think overall, these are great tools, especially for tropical meteorology. So global convection-permitting models really have the potential to make weather forecasts in the tropics much better than they currently are. We get the step change behavior towards more realism. I think they can be used for cutting edge science, like this rapid intensification study. It was kind of a byproduct, a bycatch. I didn't produce the simulation to look at rapid intensification of tropical cyclones, but because we have access to the global mesoscale, we can look at anything that we want in the output. In this case, we found that there's not just one mode of rapid intensification. Now, the last point here is that the computational cost is and will be immense. The models haven't really converged. And the question is, what science question can we address? And this is actually a question to all of you, and I'm happy to hear your feedback on that. And with that, I'll close, and thank you for your attention.
Okay, the seminar is open.
Yeah, in your marathon and sprint mode, you showed the example where one had shear and the other one had less shear. Is that generally true? Can you separate them out by shear?
Yes, so there is some overlap, but generally if you compute the mean for each group, then it falls out. I think the shear is actually a feature, not the bug in the sprint cases, because you need the shear to get these convective bursts concentrated in one corner of the circulation, and that's what the shear does. So yes, so all the sprint cases have relatively high shear.
Oh, we have a question on the slide. Great talk. Does the observation also show favorable conditions for the marathon mode and unfavorable conditions for the sprint mode?
Haven't looked into that. That's future work.
Future work.
Yeah.
Okay. Andreas?
Thanks, Falko. So you showed this comparison to ERA 5 and 3.75 MPAS. Did you consider to upscale the 3.75 kilometer model?
Yes, so it's all on the same grid.
Yeah, that
So
might
we're
help.
coarse graining the 3.75 kilometer. So yeah, all the figures that are showed in that part of the talk, they're all on a coarse grid. So it's coarse grained on a common grid. Even the ERA 5 data is coarse grained.
So you still get the stronger
yeah.
gradients.
Yes, yeah.
On the screen again, okay. All right, so you mentioned that validating these 3.75 kilometer MPAS runs is difficult because coarse-free analysis data sets can't necessarily be believed. If you use DA like reanalyses do, what do you think the impact would be on the wave structures that you see right now in 3.75 kilometer MPAS?
That's a good question. I think we would see that the model is actually representing the truth better. So if I understand the question correctly, so I'm not really familiar with DA. I'm not a DA person. I think Jared was. Maybe he means that when you do DA, you kind of get a look at the truth because you're using observations and mesh it with the model. It's a good question. I think, I don't know if Jake is around, but I think he has done DA on the 7.5 kilometer mesh. It would be interesting to compare that. The bottom line, though, is that kind of the modeling is outracing our observations. We have satellite observations at that resolution, but satellite, it's essentially just radiances, and you back out other variables. But we're lacking really high resolution, high temporal frequency of resolution on the global scale. Maybe DA can fix that a little bit, but not sure because DA is still observations plus model. So is reanalysis. That I didn't say that, but reanalysis is also a lot of the background model that goes into it. In this case, it's ECMWF with parameterized convection. So it's
Right, so
the question still is how much do we believe reanalysis?
We also have a question here from Chris Davis. Are sprint cases originating in the deep tropics, or are they more often transitioning from subtropical or extratropical cyclones?
So they're all originating in the deep tropics. In fact, all but one are cases in the Westpac, monsoon gyre cases around 16, 18 degrees latitude. That's how we start with the sprawling gyre. It's the monsoon, a monsoon low. And then you hit it with easterly shear and you get the convective burst in the southwestern corner. And I think 3 out of the 4 sprint cases are like that. And the 4th sprint case is an EastPac case. So they're all tropical. None of these are tropical transition cases or extratropical transition cases.
So all those different models, are they like MPAS and they have a uniform 3.75 kilometers across the globe?
So they're all uniform, quasi-uniform. The highest resolution is 2.5. and then there's some with 5-6 kilometer resolution, but it's all in the gray zone where you can justify turning deep convection schemes off.
And do you have any idea of what sort of a grid refinement you can do by more less core, more coarse in the polar regions, and it's
that's
so that you could see if you can. Well, for example, you get even more tropical cyclones than you had 23 by possibly accident, but I could imagine if you go to 2 or 1 kilometer resolution, you might be having more.
You would hope that it converges to the truth, but there's no way to. So I didn't show, because I only showed the 120 kilometer, the 15, and the 3.75 kilometer one. There's a 7.5 kilometers, and that's close to the 3.75 kilometer.
Okay.
So at least
There's some hints.
there's some evidence that it converges.
Okay. Well, if that's it from the audience here, I'll thank Falko again, and please join us for further